Hello, and welcome to this video on forces and elasticity, Hooke's law. This is for GCSE Physics and Combined Physics, and don't forget to like and subscribe. When forces are applied to an object, those forces could stretch it, bend it, or compress it, but only if there are more than one force acting on the object, and those forces must be acting in opposite directions. If there were only one force acting on the spring, it would accelerate. If there were two forces but acting in the same direction, the spring would accelerate. If there were two forces acting in opposite directions, the spring would compress or extend. There are two types of deformation. Elastic, this is when the object returns to its original shape when the forces have been removed, and inelastic, where the object does not return to its original shape when the forces have been removed. Provided that the limit of proportionality, more on that later, has not been exceeded, then the extension of an elastic object is directly proportional to the force applied to it. This relationship is also true for an elastic object being compressed. This relationship is known as Hooke's law and can be expressed as the following equation: F equals K times E, or force equals the spring constant times extension. The units for force, F, are the Newton, N, spring constant, K, its units are newtons per metre, extension, E, units metres. The spring constant tells us about the stiffness of the spring, how much force is needed to change the length by 1 metre. The stiffer the spring, the more force is needed to change the length, and so the greater the spring constant. When a force of 3 newtons is applied to a spring, it extends from 2 centimetres to 12 centimetres. Calculate the spring constant of the spring. First, we need our equation F equals KE. To calculate the extension, find the difference between the total length with the mass and the original length. You will also need to convert the units into metres. So we've got 12 centimetres, which converts to 0.12 metres, and 2 centimetres, which is 0.02 metres. The difference between the two is 0.1 metres. And now we can substitute that into our equation. So we get 3 newtons equals K, which is our unknown, multiplied by 0.1. Then we rearrange this equation by dividing through by 0.1, and we get 3 divided by 0.1 equals K, which gives us a spring constant of 30 newtons per metre. So it would take a force of 30 newtons to extend the spring by 1 metre. The relationship between the force and extension of a spring can be investigated using the following procedure. Set up the equipment as shown in the diagram. Add a mass to the base of the stand to prevent it toppling. Make sure that the 0 on the ruler is in line with the end of the spring. Use a set square to make sure the ruler is in the correct place. Add a 100 gram mass to the spring. Use the ruler to measure the extension and record it. Add another 100 gram mass. Record the new extension. Record the extension for the following masses: 300 grams, 400 grams, 500 grams, 600 grams. Repeat and calculate a mean extension. The safety precautions for this practical are as follows. Goggles should be worn in case the spring snaps. Keep hands and feet out of the drop zone in case the masses fall. Convert the mass into a force by using the weight equals mass times gravitational field strength equation. To make the maths slightly simpler, gravitational field strength has been rounded from 9.8 newtons per kilogram to 10 newtons per kilogram. This means that each 100 grams is equal to 1 newton. Here we've got our results table with our force going from 1 to 6 newtons, and our extension has been recorded accordingly in centimetres. And you can draw a graph of extension against the force, and we get a nice straight line here. This graph demonstrates the relationship between the force and extension is directly proportional, as it's a straight line which goes through the origin. An elastic object is one that will return to its original shape after it has been deformed. This is elastic deformation. A plastic object will not return to its original shape even after the deforming force, squashing, stretching, bending, have been removed. This is inelastic deformation. If you plot a graph of extension and force, you see that the relationship is directly proportional until, at 4 newtons, the graph starts to curve. The point where the graph is no longer a straight line is the limit of proportionality, and the relationship between force and extension is no longer directly proportional. At this point, the object is no longer elastically deformed. It is inelastically deformed and will no longer go back to its original shape. If the graph has been plotted with the extension on the x-axis, the limit of proportionality is still where the line stops being straight. It's just it will curve in a slightly different direction. Although we talk about extension, compression would give the same pattern. This is because compression and extension are both the difference between the length because a force has been exerted and the original length. A force stretching a spring does work to the spring, and energy is transferred to the elastic potential store of the spring. Before the limit of proportionality is reached, the work done is equal to the energy stored in the spring. That's calculated using the following equation. EE equals a half KE squared, or elastic energy equals 0.5 multiplied by the spring constant multiplied by the extension squared. The units are, for EE, elastic energy is the joule. The spring constant, K, that's the Newton per metre, and extension is in metres. Calculate the energy stored in the spring. Use the data from the graph. First, we need to use the straight part of the graph. This is where the force and extension are directly proportional. When the force is at 4 newtons, the extension is 57 centimetres, which is the same as 0.57 metres. Then we can use F equals KE to work out the spring constant. So 4 equals K, our unknown, multiplied by 0.57. To rearrange this, we need to divide through by 0.57 to get 4 divided by 0.57, which gives us 7.0 Newton metres. Now we have our spring constant, we can substitute that into our equation for elastic energy. So EE equals a half KE squared. EE equals 0.5 multiplied by 7.0, our spring constant, multiplied by our extension, which is 0.57 squared. And this gives us a final answer of 1.14 joules. And that's it for this video. Thank you so much for listening.